Ladies and gentlemen, also on my behalf, good morning. I will talk about the topic multifunctional reservoirs under climate change. First of all, a short introduction of the State Reservoir Administration for the colleagues that haven't been into contact with us. This is only one slide. So we are a state-owned company under the Saxon State Ministry for the Environment and Agriculture. We were founded in 1992 and we are in charge of the task for water supply and flood protection. In total, there are 84 reservoirs, 23 for drinking water, 33 for industrial water, and 24 retaining reservoirs for flood protection. And so in total, it's 536 million of cubic meters storage space. So these are the different abbreviation here. So for drinking water and industrial water. So this is very balanced. The distribution is very balanced. And we will talk also about optimization. So 1/3 share. So the optimization problem in reservoir management. So nowadays it's like this, that we have a very difficult optimization task between the optimization of the storage capacity and the optimization of the retaining space for flood protection. So many reservoirs are multifunctional reservoirs for certain different purposes. So for drinking water, for industrial water, we need a filled reservoir. So on the left-hand side, you see this for the reservoir Lehnmühle, but of course for flood protection it would be better to have an almost empty reservoir, so this is better for flood protection. So in the lower part, when you change individual parts, then you will also change all the other parts. So we found this out over the last years, especially since 2002, so that the water quality space is increased and also the retaining spaces were increased, and so the operating spaces were decreased, and so there is not so much capacity for the output of raw water. So of course we can do this in our offices to calculate this and to have an optimal strategy. So natural observations during the last years. I have shown you already the conflicts between raw water output and flood protection. And of course, under climate change, this will be even more conflict. And we could also, we have the evidence, we could prove this by calculation. So what have we observed over the last years, and how will the hydrological regime shift because of climate change? Here you can see in the first picture the seasonal cycle of the inflow to the reservoir, Klingenberg. The black columns, that's the mean long-term behavior. So we are lucky to have observation series of 102 years. So that's not always like this, but in the reservoir Klingenberg we have all this data. And the red columns, this is the behavior over the last 25 to 30 years. So the previous speakers already told about this, that because of different meteorological criteria, there are breaking points which are in the middle end of the 1980s. And you can see this here with an inner annual shifting. So the inflow to the reservoir in wintertime and spring, it will be higher. It will be increased by 25%. And in the early summer and until autumn, the inflow will decrease. So this has an effect of the capacity of the reservoirs. And you can also see the mean annual value. This has been constant so far. What else can we observe? We observe a higher frequency of flood events and of drought or dry periods. And here you can see the content development of the reservoir system Klingenberg-Lehnsmühle during several dry drought periods. So you see the lowest dry period that was used for the calculation of the reservoir system, taking the observation series into account. So 40% mean water inflow. So over a long period, only 40%. That's very significant, but you see also a green and a blue line, and you see a content decrease over a period of 9 months, a very strong decrease, more than 70% of the total capacity of both reservoirs. So 9 months, 20% inflow. So these periods, can this be compensated over a longer period or even longer periods? So these are observations in nature which are very interesting for us and which will be used for calculation. You see the black line. So this was after the flood in June 2013. So 41 months, 65% inflow. So relatively dry over a long period, 41 months. So it's not that reservoirs are empty. Of course, you would have heard about this, but you see the operating space is affected over a long period. So first calculations for reservoirs and the effects of climate change on the capacity of these reservoirs. In 2001, we started the first calculations together with the office Dr. Dittrich and Partner. We used Klingenberg-Lehnsmühle as an example. On the left-hand side, on top, you see the capacities of the reservoir system, and you see the effects of 2 climate scenarios that we used by means of the research of Dr. Enke. So this is scenario 1, scenario 2, so the possible range of possible climate changes. And the result is that even if we support the reservoir, Rauschenbach, there will be capacity losses from the reservoir system. And so the results of Dr. Enke were modeled in a precipitation runoff model. This was generated further to a long-term inflow series, and the results show that there is capacity losses of 10 to 20%. In 2008, there was the next study for the reservoir Bautzen in Lausitz, and you can see the losses in capacity 2050, 2100. They are even more significant, the losses there, 30% in 2050 and 45% in the year 2100. So more significant than the study or the research that we've done for the reservoir Klingenberg-Lehmühle. And now newer research. In 2018, we made new calculations in order to find out about the capacity changes because of climate change. We used 3 reservoirs as an example. So the reservoir Eibenstock in the western part of Erzgebirge, reservoir Lichtenberg in the mid-Erzgebirge, and reservoir Bautzen in Lausitz. And we calculated the effects of climate change in these reservoirs. These are the first results. I have to tell you beforehand that the existing climate projections rhetoric, that's what we used. So that's from the Clevis project, column or pillar C. And we used 30-year periods in order to find out about a tendency. Of course, we have a long observation period, and in order to have homogeneous time periods, and so the time periods are always 30 years long, and we generated inflow data series for 10,000 years, and the security is 99% regarding the frequency. So the water supply from the 3 reservoirs is guaranteed in 99 years out of 100 years. So these are the results for the individual reservoirs. I don't want to talk about the individual percentages, but on principle, you can see that there are decreases, significant decreases in the inflow, and for all 3 reservoirs, there is also a decrease in the capacity for the output of raw water. You can also see this in the results. What we found out regarding the real state, 1981 to 2010, so not the complete real state, but because we also wanted to use a 30-year period. So regarding the real state, there are differences between the results from Vetric 99 and the reservoirs, the observations of the actual reservoirs and levels. You can see this here for the first column. So in red, it's the observation, and blue is the results of Vetric. So you see for the inflow, these are the dark colors. So the mean inflow in Lichtenberg is pretty good. In Bautzen, there was a little bit overestimation, and in Eibenstock, an underestimation of the real inflow. But what is more significant is the lighter pink colors. So this is the capacity of the reservoirs regarding the data from Wettrick results, and the observation is very different. So you see this in Reservoir Bautzen and Lichtenberg. So regarding the Wettrick results, there would be more capacity than what we really had, in fact. So that means the inflow distributions in Wettrick are the cause for this problem. We have checked everything, the frequency, the prominent lines, and also the autocorrelation of the individual inflow months. And so it looks like that there are differing distributions of inflows from the observed facts and the Wettrick results. But still, the Wettrick results are a worthy help for us in order to estimate or evaluate the development of the reservoirs in the future, inflow and capacity for war water output. And it looks like that everything will decrease. And so we have to find more measures, more ideas, how we can prevent these problems under climate change. And furthermore, about the new results, the new study that we made, it was not only Wettrick 99, but we also used the versions 00 and 66. So the results are comparable, but of course Wettrick 66 shows more inflow, but this is the normal tolerance of natural processes, natural inflows. So the Wettrick results support each other, and we can use them for prediction. And at the end, the comparison between the observation of 30 years period and a long-term time series. So we use the inflow data series that goes back to 1961 and for the future up to 2100. So on the left-hand side you see more losses, more decreases, and in 2100, when you can calculate it, you will not use it the way as we do it now. So possible measures to compensate for the climate change effects. Already for many years, we have reacted to the possible climate change. So for smaller catchments, it's not possible, but we use the memory. For example, 3-month memory, May, April and March, for the month of June, and for 12 months. Of course, it's not for a small catchment, but we have the effect that if we have a dry period, the inflow to a reservoir can be forced to a longer dry period than what we could do with the memory. So the effect is when we calculate reservoirs by means of this approach. We have been using this for 15 years now. So the capacity reduction can be calculated already now as a preparation of a possible climate change. Furthermore, we look for breaking points. So we did this in order to find out if it still makes sense to use the inflow data series. So we found out that breaking points are always after long dry periods. So there was one breaking point in the middle of the 1930s and another breaking point in the middle of 1960s. We simulated partial series over many years, and then we had a storage capacity calculation, and so still now the inflow that we have right now, it makes sense to use the already available time series, because the inflow time series that we have, there are also the dry periods inside. What else can we do? In Saxony we have a network of different reservoirs. So the biggest reservoir, Eibenstock, is also a reservoir for drinking water. And you can use this for the Vogtland area, for the Zwickau area, for the Chemnitz area. But you can also use the reservoir of the middle of Erzgebirge, and with the reservoir Lichtenberg-Rauschenbach, you can also supply water to the Dresden area and to compensate for problems there. So to compensate for different capacities, you can use this network of the different reservoirs, and you can use it especially in the dry periods. So we want to extend even this network system. So the retaining capacity that stays in the reservoirs, so that what we need for operation purposes. So that's in dry periods, and when there is more need, you can use this, what stays in there. It's 17.3 million cubic meters per year. That's more than 50 liters per second. And of course, the biggest reservoir for drinking water, Eibenstock, has the biggest amount, so 60%, this biggest share. Of course, we can also use support from other reservoirs, so that we buy water. For example, we have now the general refurbishment of the reservoir Lichtenberg in the years 1921, 1923. Then the reservoir Rauschenbach has to substitute this reservoir, and then it might be that we need support from the Czech reservoir Fly. What else can we do to compensate for this? This is a very good example. So that we have a transition of the reservoir Gottleuba. So there is the capacity regarding observation, 254 liters per second. And when you transfer the catchment of the Mordgrundbach to there, you can even increase it by 22%. So it's more than 50% of the reservoir. So to transfer water from other areas is more effective than to have a bigger amount in the reservoir itself. So the inflow is more important than the use of the content which is inside. What else can we do? So to build new reservoirs, construction of new multifunctional reservoirs, bigger basins, more than 1 million cubic meters. So we already put Launstein and Glashütte into practice. Niederpöbel is under construction right now, and there are more retention basins that are planned and that we want to do the construction in the future. These are big retention basins. You see on the right-hand side, you see the construction site of Niederpöbel, and at the bottom you see Launstein. So this was planned as a big drinking water reservoir, but now it's a multi-purpose, multifunctional use. And at the end, you see the map. It's almost 60 years old. You see the Upper Elbe and the Mulde. You see planned locations for drinking water reservoirs. So there were already plannings for this, for new reservoirs, also some years ago. So building new reservoirs. So these are not easy procedures for applying for this. And the last slide about water quality. So I'm a representative for water quantity, but I also want to talk about water quality. So for the real state right now, and also for the future under climate change, water quality plays a big role. So I have only one slide about this that shows you one effect. You see the times when the ice breaks up and when the layering starts, and we used meteorological data, inflow data. So also this data shows comparable time periods with the breaking points that we found out. So the layering starts 2 weeks earlier, so you have longer periods where the hypolymion is used in reservoirs, so the good cold water from which is deep down. So you have to live longer with the hypolymion in the water supply than before the breaking point. So this was my presentation. Thank you for listening. Thank you, Mr. Winkler. Questions? So maybe since you are a specialist about water quantity and not so much about water quality, but the last item you talked about water quality. So in Saxony, we have problems with eutrophic, and we know what happens when water reservoirs overheat. So what is your approach with the increasing summer temperatures and the problem of eutrophication? So maybe I can ask Thilo. I forward this question to Thilo. Maybe he can answer this question much better. So Professor Matschulat, could you make your question more detailed, more clearly? Of course. So we have increasing temperatures in the water body. So according to the Henry law, there is less oxygen in the water body, and even if the nitrous supply into the system is the same, we have higher risk for eutrophication, and all the microbiological composition plays a role in this. So my question is, if you have the same approach as Mr. Winkler has this for the water quantity, yes, we calculate this. Also, what means criteria of water quality. The Saxon reservoirs do not have this problem because we have a decreasing nitrous input, and we have refurbished catchments so that the sewage problem, phosphor, is decreasing. We have long-term time series that show that the phosphor input decreased by 60% compared to the GDR reference time period, but still we observe significant changes in the biological structure of the reservoirs because of climate effects. It's hard to differentiate between the climate effects and the classical eutrophication effects. What is significant, because you talked about the oxygen composition, so we have metalimnic oxygen deficits. But we think it's because of the climatic effects, because of the phytoplankton structure, the changed turbulence structure at the water body near the surface. So we think, and we can also prove it, that the eutrophication tendency in the Saxon reservoirs is actually decreasing. It's still decreasing. Mr. Winkler, I have two questions. What is the minimum amount that you used in your calculations that the reservoirs should output? And when you were talking about raw water, which is decreasing, this is a theoretical value. So how did you use or utilize the raw water output? So the minimum water output was determined in the middle of the 1990s, and there were the plans for water management and so on. We applied for this. So there was a formula that we used then regarding hydrological, morphological aspects. So the minimum quantity for output. So there were many small reservoirs where we had a minimum output 0, but we increased this of 10 liters per second up to 20 liters per second. Reservoir Eibenstock had 50 liters per second, and this is now 500 liters per second with a catchment of 200 square kilometers. Regarding the utilization of the reservoirs, the drinking water reservoirs, we have to differentiate this in the different regions. So the Chemnitz area, when we have the sum of the reservoirs, we have a utilization of 75% of the capacity, and in the Dresden area, it's a utilization. Of course, it oscillates and it changes. So there is a utilization of 90 to 100%. And what I showed to you, the output capacity, that's the calculated total capacity of 99 utilization. Maybe 2 more questions, because then there will be the coffee break. My question is towards adaptation measures. So you already showed that the transfer from other water bodies is a good measure, but you need a minimum quantity of water for this. So did you research if this will be possible in the future when you look at Wedrick? Also the water bodies where you want to take the water off, they will be drier. So you are right in this. This is true. So the capacity of the reservoirs will decrease. And then, of course, also the other water bodies will decrease. So this must be calculated according to the Wedrick scenarios. This was only an example to show how to increase the capacity in principle, as it is now the real state. So this Mordgrundbach has 13 square kilometers. When you do the storage calculations for climate scenarios, you have to do this for the whole catchment area of the reservoir and of the other water bodies. And one more question. One of your first slides showed that during spring the inflow will be higher, but this is a contradiction to the precipitation data that we heard about in the last presentations. Is this because of melting of the snow? Yes, in the spring month, especially in the mountain area. This was the example of Klingenberg. The Wilde it's in the eastern part of Erzgebirge, but this will be the same for other reservoirs. The runoff regime from the flat area is shifted to the mountain area, so you have a steady alteration between melting snow. So you have a runoff regime, what was typical for the flat area before. So it's a combination of melting of snow and precipitation. So we are back at climate change, and there are many more topics to talk about this and adaptation measures that we have to calculate and improve during the next years with new data, new models. And it's good that Saxony has a good network of reservoirs so that we are still flexible. Thank you, Mr. Winkler, for your contribution, for your presentation. So there will be the coffee break now. So I propose that we continue at 11:45 with the next presentation, or maybe 11:40, so to save 5 minutes. So now coffee break, and we come back at 11:40 for the next presentation. Thank you.